a continuous well. If you have checked Odell, then you will see that I've put your course outline there, and I've also put some notes. It may not be the notes that I'm using here, but it's notes that will also help you because it has statistics and a summarized form of what we are discussing. I'll also upload this one because the good thing with the notes right now is I've just found them. They have enough examples, so I'll be uploading this to you as well. Yeah, so we have sample spaces, and already you know what we mean. Like if for example, you are tossing a die in example 1.6, you see that the possible outcomes are 1, 2, 3, 4, 5, 6. Each of these values in the within the braces is called a sample point. Sample point. Yeah. Now, you've come up with 1, 2, 3, 4, 5, 6. If you want a sample space of all the possible outcomes. Yeah. Sometimes you may also have, maybe when you're performing an experiment like that of tossing a die, you, yes. Somebody else asking a question. You can form another sample space if you're only looking at the outcome of odd numbers only or even numbers only. So you then have a sample space of two possible outcomes, an odd number or an even number. So if that is what your objective is, just looking at whether a number is odd or even, then you can see that your sample space reduces from 6 points to only 2 points or 2 sample points, odd, even. But this doesn't give you enough information. So sometimes when you're looking for a sample space, we look for that which gives us a lot of information. Yeah, and you can see even this guy, he says that, for example, if this one, the one that has odd and even, may not help you if you wanted to know if the outcome you have is divisible by 3, because nowhere has it mentioned 3. Yes, we know 3 is odd, but how does that help us? We don't know the number that's coming up. We just know it's an odd number or it's an even number. But is it divisible by 3? You cannot be able to tell that. So the better sample space to deal with is this one that is more informative. Yeah. So pick a sample space that's more informative, because then from there you can derive more information from there. From here you can even find the probability of getting an even number and the probability of getting an odd number, the probability of getting a number less than 4, the probability of getting a number which is divisible by a certain number like 2. Yeah. And then you can also even do sums and many other things. So you can gather more information from a sample space that gives you all the possibilities like this one. You can actually form some subspaces, some sub-sample spaces. Yeah, in fact, yeah, then you have an example 1.7, which may, well, all right, that may not help us in any way possible. So let's go down to some few other ideas. Any question up to there? This table here, or this graph that you see here, simply is based or derived, derived from example 1.7, where you have a coin. When you have 2 coins, or when you toss a coin twice, then the possibilities is you can have, if you have called the head 0, then this would probably represent the 0, 0 here represents head, head. This is tail, head. This is head, tail. And this is tail, tail here. So you've just changed to numbers. And the good thing is when you change it to a number, then you can put it in a graph like this. So this graph is just a depiction of the sample space of tossing 2 coins. Yeah. You know, you just do anything that can easily give you more information. Yeah. So maybe we can come across this as we go down a little bit. You see how putting it in a graph like that can help in any way. We have already said that a sample space can be discrete or can be continuous. Discrete if you can count. So if you can count stuff like natural numbers, 1, 2, 3. So we have finite sample space. We have countably finite sample space. This one here. Those are the the three that I want to, and then we have uncountably infinite sample spaces. Finite sample space is like that one of the coin. That one you can count, yeah, or a die, or any other experiment that you can easily count the number of outcomes, 1, 2, 3 up to some point. So we call those one finite sample space. There is also another one which, yes, it's countable, but you don't know where to stop. So like you have natural numbers which start from 1 to infinity. So you don't know where to stop exactly. But if you look, you can actually count. So you can do 1, 2, 3, 4, 5, 6. It's only that you don't know when to stop. But since you can count like that, 1, 2, 3, then we call them countably infinite sample space. Yeah, that means it has as many points as there are in some interval on the x-axis. Okay, then we have this. If within a small interval like 0 and 1, you have so many values within that interval, and it's called a non-countably infinite sample spaces. Yeah, and an example is if you're measuring the weight of people, even the weight between 80 and 81. People who are between 80 and 81 kilos, and if you're measuring maybe to a decimal place or 2 decimal places, maybe one is 80.01, 80 points, or if you're counting to several decimal places, if you have a very accurate machine that can measure maybe say up to 10 decimal places, so that you can have somebody of 80.0000001, 80.001001001. So you can have so many in between that small gap of 80 and 81. So that forms a non-countably infinite sample space. Yeah. So a sample space, therefore, where you can count stuff. If you can count whether it's finite sample space or countably infinite, we call that one a discrete sample space, as long as you can count. But if you cannot, then we call it a non-discrete or continuous sample space. Yeah, non-discrete or continuous. The word continuous is not mentioned anywhere, but you will see in some books they call it continuous sample space, non-discrete. And then you have events which are just nothing but part of the outcomes. Like if you're tossing a die, and you just want odd numbers only, then you see that's like a sub. Those activities within the experiment, so specific outcomes within your entire experiment will form events. What is the event that the number that comes up is even? What is the event that the number that comes up is odd? So events are just a bunch of subset of the total sample space, which you are focusing on. Yeah. Let me use an experiment that I was using last week, which was weird, but I'm sure it helps some people. If let's say you are at your balcony and you are dropping eggs. Yeah. Last week it was about you jumping. Today let's just give a twist, a little twist. So you have eggs, or you have something that you're dropping to the ground, and you want to see whether it's going to break, whether it's going to remain intact, or whether it's going to, And when it breaks, does it break in one place, or break in several places, or does it splatter? So if you're doing an experiment like that, of dropping either a stone or an egg or something, and you want to see how it breaks, your method focuses on one event. The event that whatever you're dropping is not going to break. Yeah, there's a possibility that maybe if you drop I don't know, you might drop an egg and it refuses to break. Maybe I know that's an impossibility, but why not? You don't be surprised if one of these days an egg drops and it refuses to break. So that's a possibility. So you might be looking for, or you might be looking for an event that when I drop this egg, It lands without breaking. So you see that landing without breaking is is one of the possible outcomes. But you're just focusing on it. So that's an event. Yeah. So an event consisting of a single point of S is often called a simple or elementary event. If what you are focusing on only happens once, like if you remember for the coin, there's head, head, there's tail, head, head, tail, and tail, tail. So you may be focused on an event of both coming up tails. And you can see from the sample space of 4, where you have head, 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 tail, tail, head, and tail, tail. Tail, tail only happens once. So such is called an elementary event. If it was a coin twice, the event that only one head comes up is the subset of the sample space that consists of 0.01, which is head tail, and 10, which is tail head, as indicated. So back to the graph that came up at some point. So if you are to represent using a diagram, you can see that this shaded part just represents the subset where you only have tail head or head tail. That's just a pictorial diagram, just to help you maybe be imaginative. Now, no question up to that point. Some few things to note. Any question?
Excuse?
Yes.
Yes.
Yes, go ahead.
What is the difference between finite and infinite sample space?
Yes, what is the difference between
Because
finite? Yes, yeah, go ahead.
Because both of them you've said they are countable.
Okay. I'll just go. Oops. Oh. Making me a sun. Okay, anyways, I'm looking for it. I said we can have finite or finite. Some people say finite sample spaces and infinite. Finite means you can count. You can count them. Infinite, on the other hand, you cannot count. That's the difference. That's basically the difference. Finite means you can count. Infinite means you cannot count. Am I answering your question? Ama ni mimi nilikuwa nimesema vibaya?
I'm getting confused juu hapa hivi kwa discrete sample you've said a sample space that is finite or countably infinite is called discrete. Means
I think I get, yeah, I don't know where I've said that. Let me just take you to where I think I mentioned something like that. Yeah, I think this is where I told you. So we have finite sample space. This is a sample space where the number of the possible outcomes there are not too many. You can count and finish them within a given short time, a measurable time. Yeah, like if you have 2 dice, you toss them, the sample space will be 36 because you can have 1, 1, 1, 2, 1, 3. So 36, that's a number you can count. You may take some bit of time, but at least within a given time frame, you can count. Now that's finite. And so because you can count, it falls under this category called discrete sample space. Now that there is what we call countably, underline the word countably. Countably infinite sample space. Countably means you can start counting, that the time frame, we don't know when you're going to stop, because the numbers to be counted are very many, but you can still count. Say maybe you're talking about the probability of getting a Kenyan. Let's say you're counting Kenyans. Yeah. So you want a sample space. So you're taking an experiment where What experiment? I'm just thinking of an experiment that can involve all Kenyans. Okay, think of any experiment that you can do that involves all Kenyans. Now, in Kenya, right now, I guess we are somewhere around.
Huduma namba.
Yeah, I'm a Huduma namba, yeah? So you want to find out the people that have Huduma namba. So, you see, these are people you can count. It's possible to count the number of people with Huduma namba. Lakini, the amount of time you will take, the time frame, will now make that to look like it's infinite. So it's countable, yes, but the time frame is very infinite. You don't know how long it will take, so much. So it still falls under discrete sample space. Yeah. But then they are now something called uncountably infinite. Uncountably infinite is now something like what I told you. If now you want to take the weight of all Kenyans or all people on the planet, and you have an instrument which can measure accurately up to 10 decimal places, then you can be sure that even between a certain weight, like let's say 50 and 51 kilograms, you can get so many millions of people in there if you're counting across the globe. So you can have millions of people just within 50 and 51 kilograms fitting there. So that's why we are saying such a situation is uncountable, uncountably infinite, or uncountable. You may not count. I don't know if that makes it a bit clear. But when you talk about height, the height of people, the height between a two all numbers, they're in between. You have point something something, point something something, point something. So that point or those fractions make it difficult to do as proper counting. Yeah, so that is what we call an uncountably infinite sample space. Sijui kama nimekujibu vizuri ama just confirm.
Understood.
No, be honest. We will stick there mpaka ushike. Uko sawa?
Nimeelewa.
Hiyo ni poa. Yeah. Usiseme tu ni poa ndio tuendelee. No, we cannot continue. Tunataka watu washike hii maneno. So kama umeshika hapo sawa. So let me go down back to where I was. So I'm here. The good thing with these things that these 4 things. If vitu nne hapa unaona hizi nimewacha niweke. Yeah. The 4 that I've highlighted. Uzuri ya hizi vitu ni all of you have done discrete structures. You've done sets. Okay, it may not be in discrete, but I'm sure you've all done sets. So there's something called union of sets, intersection of sets, and the complement of sets. So we use that language of sets to describe some operations on a sample space. So the sample space S, look at it as if it is the entire set or the universal set. For example, 2 coins, when you're tossing 2 coins, you have head, tail, head, and tail. So that is S. So the elements are those ones I've mentioned, the 4 elements. So it's a set with 4 elements or a cardinality of 4. Now, consider 2 events within the sample space. Let's say, I've just seen. It's a nice one. So consider for those 2 coins, hapa chini. Yeah, so look at this example 1.9 so that we can understand this. First of all, we know, for those who have forgotten, a union, when you use this U kind of a thing, it's a union. So union means you bring the elements of one set and another set, put them together. Intersection means it's only elements which are common to both. That one you know. Then we have the complement. When you say complement of A, you're simply referring to members or elements which are not in A. So when something is in the complement, it's outside the set. And then the difference. Again, if you have forgotten, the difference of 2 sets, when you say A minus B, for example, number 4, then you simply are saying you are looking for the elements which are in A. They probably also might be in B. Sorry, elements which are in A, but they should not be in B as well. Yeah, they are in A but should not be in B. Yeah, so A complement is the same as all that is in subtracting the events of A from the sample space. Anyway, there's an example here which can help us. Let's say A. This one represents at least one head occurring when you toss 2 coins. Yeah, at least one head. At least means it can be more. You understand also the language, yeah? At least. At least. Yeah, that's the statement that most of you sometimes misuse. Yeah. Mtu akianguka lazima at least hajaumia. So at most ulikuwa na expect at least. You know, you guys mnajua vile mnatumia at least. At least. So that means that is on the list on the yeah, so at least simply means it can be more. At least hajaniona. Yeah, kama unaepa at least hajaniona. So it means at the least hajakuona, but at most they could some other things could have happened. So at least means there is only one, and there is one, but it could be more, and that's why you have these possibilities. There is head, tail, tail, head, head, head. Now event B, we have chosen event B. So A is at least in A, at least one head occurs, and then event B is a situation where the second toss results in a tail. Yeah, that means if you have, recall your sample space, there was head, 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 tail, tail, head, and tail, tail. Those are the 4 elements in the sample space. Now, if you're looking for event A, where you only have at least one head, then these are the outputs. Then if you're looking for event B, where you are ending with a tail, then this is the sample space. So those are the 2 different events, A, B. Now, if we play now with the unions, the intersection, and everything, which means A union B is a combination of what you have here for A and combination of what you have. And remember, you don't repeat elements. So since these 2 elements or these 2 sets are not the same, you can then combine all of them. HT, TH, HH for A. Oh. Where is HT? Yeah, HT, TH. Well, HT is common. HT is here and here. So we don't repeat elements. So we just write HT once. In fact, HT therefore should be in the intersection. Yeah. Here in the intersection is what is common. HT is common. So what is common is in the intersection, and in the union is a combination of everything, which is here and here without repeating. Then A complement is, what is it that is not in A? And you can see that apart from these 3, the TT is not there in A, so it is in the complement. And then you have A minus B. A minus B means, first of all, it is all which is, you must have everything in A, but remove anything that is in B. If there is any of these 3 that is found in B, remove it. So you can see that HH is not in B, TH is not in B, but HT is in B, so we are going to remove it in the subtraction. So A minus B will then just remain with TH and HH. Okay, so that's how to play around with sets or sample spaces using the knowledge of sets. So if you thought you may never apply sets, there you go. Come across them, and you'll come across this as we go along. So that was basically just to make you understand how to use the idea of sets in sample spaces and in events. There's something here called disjoint. If this thing, sorry, I overlooked that. This here, where you have null. If there is nothing common, if the intersection of 2 events is empty, it means they don't share anything. So they are disjoint. Disjoint events don't share anything in common. I don't know what would be disjoint for us when we are tossing a coin. Let me see. Events that can be disjoint. Well, maybe in an example that we come across later, then we will see what disjoint is. But just get to know that if two events don't share a common outcome anyway, then we call them disjoint. Okay, again, any question up to that point? Ikifika 3:10 because tulianza 3:15 tunasimamia hapo. As I promise, I will only be using 1 hour for our online classes. And we are reading stuff today because we are just starting, but from next week, we'll be looking at examples. So I'll be picking an example, we work on it. Example, because the more we do examples, and because you have the notes, you will be reading for yourselves. So just make sure you read. That's where the problem is. Some of you mnaweza ingia tu sasa tunafanya examples peke yake examples. So you are very good in examples lakini hauna theory. So you need a theory. That means you will read for yourselves. Tukikuja class, let's do the better job of going through examples because I know sometimes we are very good at theory. Lakini ukifika kwa exam room unapewa swali na unachanganyikiwa. So we will spend much of our time online to just working out problems. So we look at nice problems, not simple problems. I'll also leave simple problems to you guys. But I'll be picking examples that are a bit challenging. Then we go through them together. Now, there are two approaches. What you see up here just simply tells you that probability can be measured in percentage or within a range of 0 to 1. And I think here tulisema last week. So you can give your probabilities as anything between 0 and 1. 0 being the least possible. That thing may not happen. Will not happen if it is 0. And then if it is 1, if your probability is 1, then that surely will happen. And then if you're not very sure, maybe not, then it may lie between 0 and 1, 0.5, 0.1, 0.2. Yeah, and you can give it in percentage. Just multiply whatever you have in between 0 and 1 by 100. Yeah, then we'll give you in percentage. So 1 is 100%, 0 is 0%, 0.5 is 50%, a quarter of the thing is 25%, a quarter is 25, three quarters is 75. Well, that's how it goes. Then we have what we call the classical approach. It's good to understand. Somebody may ask you to differentiate between these two, classical approach and frequency approach. Hizi vitu mbili. Yeah. And it's as easy as you can see. Classical approach is, let me use tossing a die. Now, when you toss a die, dice, I don't know, die is the plural or whichever one, but that's dice. When you toss a dice, ukirusha dice, then you want to imagine that the numbers 1 up to 6, they come up equally, or they have equal chances. You give them equal chances. So if they have equal chances, then the probability of any of those 6 numbers appearing is 1 out of 6. This 1 over 6. If you're looking at a coin, then you are imagining that because there are only 2 possible outcomes for a coin, then they are equally possible. So heads has 1 over 2. Tails has 1 over 2 as well. You never know. Maybe heads, actually, if you toss a coin and you count the number of times, maybe it gives you 1 over 4. And the other one, the remaining, you do 1 minus 1 over 4. That's 3 over 4. So in classical approach, we assume that things happen in equal or equally likely. So that if an event can occur in H different ways, take for example the coin, an event can happen, heads can happen. Let's toss a coin. and look at the event of heads coming up. Let H be the heads coming up. So if an event can occur or heads only has one chance out of 2, where n is 2. N is the number of possible outcomes, or the number of ways you can do that, which is 2. So you can have 1/2 for a coin. If it's a die.
Me, sir.
Yes.
Mwalimu.
Yes, nakusikia.
Screen PowerPoint sijui inaonyesha aje. Haionekani poa.
Ni ndogo sana.
Yani iko blur.
Iko blood.
Yes.
Okay, so nataka aje ni expand.
Maybe ni issue iko side yake. On my side it's okay.
Hebu refresh screen yako.
Me too.
Okay, wacha nifanye head count haraka ama voting haraka. Because I don't want to disadvantage anybody. Give me a thumbs up if you can see my screen clearly. I want to count 1, 2. Yeah, inajicount too. So many people. Okay, do this. Weka mkono juu because mkono ndio I think in account. Don't use the thumbs up, use mkono, yeah? Those are 3, 5. That's quite a number. Haya. Yes, 16. Bana mko wengi. So which means hapa hatuna shida. Kama screen yako iko shida. Haya, wacha tu count pia. Okay, thank you. Thank you for the hands. Thank you. Thank you very much. Weka chini. Mkono iende chini because I want to count the guys who have a problem. Nakoli, weka mkono chini. Yeah, thank you. How many have a problem with the screen? Julius Omukatia. You are you are a lone ranger. So maybe Julius, you can refresh your screen, eh? Nakoli. Wewe uko kila mahali. Ulikuwa, eh? Nakoli, I'm not understanding you. See, 1 minute right now you ulikuwa unasema unaona. Which is for you? Yeah, Nakoli, which is which? Because your hand is up everywhere. Are you?
Yes, sir.
Yes.
Actually,
Yeah.
like people are sharing. Some people are sharing this an account. Some people have been deregistered, so they can't get access to the class, so they are sharing account.
Oh, is that why there is a problem with the screen?
I don't think.
I don't think it affects, yeah?
Yes.
Okay, fine. If you have a problem with your screen, just refresh your device. Yeah, you'll see whether it can fix the problem. If it can't fix the problem, then you can maybe share with someone. In fact, if you guys are tech savvy, there's an application called AnyDesk. No, not AnyDesk. I'm sure you can find a way of sharing the screen with your colleagues. Yeah. You are IT guys, Ben, and nowadays, so many of you are tech savvy. Yeah? You can even listen while you are in blankets and listen to me clearly. Based on technology. Yeah. So let me move on swiftly because there is an amount of information I wanted you to get today so that next week we pick another. So right now we are differentiating between classical approach and frequency approach. Now, classical approach, we have said, if you know the sample space or the elements within the sample space, then the sample space will form the denominator of whatever you're doing. So if you're tossing a coin, your sample space is 2. So the denominator of a fraction you're going to give us as your probability will have 2 at the bottom, and at the top, the numerator is the number of possible ways that whatever you're looking at can happen. So if you're tossing a coin, there are two possible outcomes, but then heads appears once. Yeah, there's one possibility, or there's one likelihood that head comes up, and there's one likelihood that tail comes up. So that's the classical approach. Now there's another one called the frequency approach, where now you need to do an experiment. You need to, do an actual experiment several times. So like now, before you say the probability of getting heads when you toss a coin is half, we say no. You do an experiment, and in fact do it over and over. So you can maybe do around 1,000 of them. And there is an example here of somebody who, yeah. So look at example 1.11. This explains frequency well. If we toss a coin 1,000 times and find that it comes up heads 532 times, because you agree with me that it will not be 500. Yeah, if you do an actual experiment, then your imagination would think that maybe there will be 500 times that the heads come up, then there is another 500 times that the tails come up. No. You may find that the heads come up 532 times, which means the tail will come up 468 times. Yeah, 460. So they are not equal. So you will then find out that the probability, therefore, of heads coming up is 0.532 instead of 0.5 that you know. Yeah, in classical, it is 0.5. In frequency, it is 0.532. The tail is 0.468. So you see now this is more specific, and it is based on an experiment. Yeah. So the classical, it assumes it is equal. It has equal chances. So if we were to go by classical and we do toss a coin 1,000 times, then surely we should find 500 heads and 500 tails. That is not the case. So that's why they left that. They no longer use that assumption. Now they go to the frequency approach, which is more practical. So and then again, the problem with this is if you repeat the same experiment, you will not again get 532 times. Yeah, for the head. You may get a different thing. You may even find out that now it is the tails, which has 532 times instead of the heads. So both the classical and frequency approaches have serious drawbacks. I hope you understand this term, serious drawbacks or disadvantages. The first one, which is the classical, is because it assumes that everything is equally likely. Yeah. The next one of frequency also has a problem because you don't know how large you should, or how many experiments, or the number of tosses you can do. For example, if it's a coin, for you to, because if you do 1,000, you may get 532 times, which gives you a probability of 0.532. What about if you do 10,000 times? Yeah, you may come across a different probability from the one that you got when you are at 1,000. So again, that's a problem. Yeah. So anyway, we use them, but you need to know that those are the problems. So we still use all of them. We use the classical approach at some point. In fact, much of our discussions, we use that. We also use frequency approach, particularly if you have experiments you're doing. All right. So so I wanted us to reach the axioms today and properties, so that next week we pick on examples. Some few axioms. Another term for axioms is just what? Some terminologies are very complicated. Just look at it as some outcome or something that we can conclude. Or in conclusion, that if we have a sample space, okay, let's just go to axiom number 1. If you have an event A in the class C, then the probability of A. Okay, I think you need to go back to understand what that A is. Just slightly back. So suppose that we have a sample space S. By now you know what a sample space is. If S is discrete, that means the elements there are, we can count. All subsets correspond to events. All subsets. Like if you want only tails, that's a subset of S. If you're tossing a die, you may only want odd numbers, which is 1, 3, 5. That's a subset of the sample space. So we call them events. So all subsets correspond to events. The event that it comes up odd, the event that the number is coming up is even, that's an event. But if S is non-discrete, that means that we cannot count, then only special subsets called measurable correspond to events. Yeah. Yeah, like the one I was telling you, if you drop an egg, if you have, and then you're considering all possible outcomes, and if they splatter, to splatter ni kutapaka, splatter. If you hit the ground and the egg splatters, you may also want to know how far it splatters. Another one may splatter and just remain there as a solid mass. Another one will hit the ground and then splatters, draws a line. Another one splatters, it forms something like a star. You know, it hits the ground and forms all sorts of shapes. So imagine maybe you are focused on the shapes formed when the egg splatters. How many shapes do you think you can come out with? Very many. Yeah. So even some two shapes may be the same, but not the same, not the same size. It may form something that looks like a starfish. But then one is longer than another one. So those are very many possibilities if you're looking at the shapes formed when it splatters. And you can do that experiment, by the way. You can do, if you have enough eggs that you can drop, or if you have enough stones or anything that you can drop and then it breaks, you can try to take photos. So every time something falls, you take a photo. Another one falls, you take a photo. And then you go through the photos. Those photos may all be different. It could be 1,000 photos, but the way it has fragmented or the stone has fragmented is totally different in each of the photos. Or you may be lucky. 1 or 2 may look exactly the same, because there is also that possibility. So those are called, the entire thing you're doing of dropping a stone is the experiment. The outcomes, we can call them events if you're looking for specific type of outcomes. Yeah, the specific type of outcomes you're interested in form what you call the event. So to each event A in the class C of events, we associate a real number PA, which is the probability function. P stands for the probability function. And P is called the probability function, and P is the probability of the event A. If the following axioms are satisfied, or if the following things can be satisfied. So for every event A in the class C, the probability of A is either equal to 0 or more. In fact, let me just jump down a bit into a nicer way that they have put these actions. So don't worry about so much, because I don't want to bog you down. Let's come down to the theorems, because one of the things that you need to know according to the course outline is you need to know the theorems or the properties of probability. So here, theorem 1.1 says, if A1 and this is supposed to be whatever this is. So if A1 and A2 are events, if A1 is less than A2, or if you have two events, A1 and another event A2, where A1 is less than A2, then surely the probability of A1 should also be less than. Upper katikati, here in the middle, they have put something wrong. It should be less than or equal. That should be here. So put that in your mind. Less than or equal to. So if that is the situation where if A1 is less than or equal to A2, then also the probability of A1 should be less than or equal to that of 2, probability of 2. Yeah. So this is a property you need to keep in your mind. Somebody's asking a question. For event A, the probability of any event should lie between 0 and 1. I think that one is straightforward already. Now that one is something you've established. The probability that whatever you're looking at is impossible to happen is 0. Yeah, this is an impossibility. When you see the probability of null set is the probability of an impossibility. Yeah. Does it mean that it's impossible to toss the coin? Or is it impossible to have any of the outcomes that we're looking at? If you throw a die, why would it be impossible to get any of the numbers 1 up to 6? Yet it's already there on the faces. So this simply means an impossibility that if you toss a die, for example, it's impossible to get any of the numbers that we know on the face. So unless by magic the thing disappears, all the faces disappear. So that is what this means. So get this as your number 1. This is your number 2, number 3. There should be a number 4. I hope it is down here. Yes. In fact, oh, it even has up to 5. That's okay. Now, let me repeat what I'm doing. One of the questions you may get, underline may. Yeah, I'm not saying you will, you may. Is a question that asks you for okay, we call it the axioms, you can call it the properties, or you can call it properties. Mostly we call them properties. So you could be told to outline maybe 4 or 5 properties of a probability model. So one thing you will know is that the probability of A, the first one that we saw there, is either equal to 0 or more. Is equal to or is greater than or equal to 0. In other words, we sometimes call it a negative probability. Then the probability of an impossibility, or the probability of the null, is 0. Surely, if you are doing an event or an experiment, if you are performing an experiment, then there are some, you cannot say it's impossible. If you are dropping eggs from some stair or some upstairs building, yeah, unless the eggs get suspended somewhere in the middle by some witchcraft or something, it fails to land. Surely must get an outcome. All right. And the probability of getting the sample space, these are the point now. You go happy. Oh well, I don't see. There is one which I'm not seeing here. I don't know why. Did we skip it anyway? Let me see. Oh yeah, this one. If the events we are looking at are all from the sample space, then the probability of the sample space is 1. I hope that is clear. The probability that all the outcomes within the sample space will take place is 1. Yeah, if you do the experiment, then surely you are not going to miss out on one of those possible outcomes because they are all in the sample space. If you tell me that if I toss a coin or 2 coins, I'll get head-head. Yes, head-head is part of the sample space, so that one will surely be there. If it is head-tail, it's part of the sample space, and it's going to be there. So the probability of getting something which is in the sample space is 1. You must get one of those outcomes. Yeah, this point should have been listed here as one of the theorems. So remember that. If you're asked for the properties, include this one also. Include this one. Then you also have this one. Then you go down. You have this one of impossibility. Then you go down. That if A is the complement of A, then the probability of A complement is 1 minus the probability of A itself. Yeah. If the probability that you've invited a visitor, if the probability that they are not going to come is 0.2, then you can see that the probability that they will come is 0.8. Let me repeat that. if you're having or waiting for a visitor and you know that the probability that they are not going to come is 0.2, then it means that the probability that they're going to come is 0.8, which is simply the same as saying that the probability of the visitor not going to come, which is A complement, is the same as 1 minus the probability that they are going to come, which is 1 minus 0.8, which gives you 2. So that should be clear. Then this last theorem here for today, and it's the last thing I'm mentioning today before we call it a break, is if you have several events, A1, A2, A3, up to A4, all of them within a sample space, then and you want to unite, then the probability, then A union A2, all is uniting all the events. Okay, sorry, where all those events are mutually exclusive. Mutually exclusive simply means that they don't share anything in common. They are disjoint. They don't rely. I mean, the outcome of one does not depend on the outcome of the other. Then you can add their specific probabilities. Yeah, you can add the specific probability. That means the probability of event A happening is just the addition of the specific probabilities of each one of them. And if A is the sample space, then they should add up to 1. Those probabilities should add up to 1. And if A and B are any two events, then the probability of A union B, is the probability of A alone plus the probability of B alone minus what is common. That's what we normally do even when we're uniting two sets. The union of sets, if you're uniting two members of sets or members of two sets, you try to exclude those ones which are common, or those ones which are in the intersection. So this is a very important expression that you will still come across it so much as we go along. So for today, okay, well, you can extend the others. So I'm going to send this thing to you in due time. So look at it. But that for, so when we come next week, this is again, that's just for your own good. Now, when you come next week, then we look at other things, including the tree diagrams, conditional probabilities. Yeah, so we'll start, this is where we'll start next week. Conditional probability. Yeah, conditional probability. Any question? Yeah, so as we continue, we'll also talk about things called tree diagrams. A tree diagram just is a graphical depiction of some of the dependent and independent events. I'm sure some of you are familiar. If you did Form 4 well, you must remember some tree diagrams that we were using.
Excuse me.
Yes.
I was asking.
Yes.
Where specifically are you going to upload the notes? Is it in Odell or Martin?
I've already uploaded in Odell.
Oh, okay.
But for this one, I haven't. The one I've uploaded in Odell is a simpler. So I want you to read that one first because it's just notes, but it's kind of simplified. After you have done that, then I'm going to also give you now. This is more of the one I'm using now. As you go along, it's just examples, 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 and examples. So I want you to get to the examples after you read what I've sent first, which is already in Odell. It's already in Odell.
Excuse.
Yes.
I've logged into Odell and I cannot find
it. How now? The morning group were able to see because we are using the same. It's a same document with the morning class. It's only that you need to pick what is relevant to you. Nane mwingine amelogin na akakosa. I want to know if the problem is one person or.
Is it BIT 210?
It's BIT 210, yes.
Yeah, I'm in there and I cannot see anything.
Bana. I'm also in there and I see what I've uploaded. In fact, I've uploaded two documents. Kuna course outline. Can you see the course outline, which is in Word document?
No, it's empty.
End up, where are you looking? You go to announcements. Can you see where announcements are?
Yeah.
Yeah, click on announcement, then you will see a Word document and a PDF.
Oh, I've seen.
Word is, yeah, you've seen?
Yeah, I've seen.
Yes. So go there, even the other person who's not seeing, just go there, look at announcement. There'll be a Word document, which is course outline, and a PDF, that is the notes. Yeah, thank you. At least one person has confirmed. Any other concern? Any other concern? Was up to there. I think we are good to go. Remember, your course, your attendance is always recorded. So okay, attend. Somebody is going to download your attendance somewhere. So make sure you're always there. Those of you who are having a problem, I hope you'll also fix before we meet next week, so that you don't need to struggle sharing screens. Thank you very much. See you next week.